Okay, so this is another conceptual question where we're going to kind of look at our general equations that we have for an object moving with simple harmonic motion and what happens if we manipulate them in a certain way. So we want to know what happens if the amplitude is doubled, what happens if the total distance, what happens to the distance that it travels, and then what happens to the period, and what happens to the maximum speed of the object. So period, like we talked about before, is a measure of time. And it's time to complete this single cycle, right? So if I have, for example, a sine function, right, and I start at t equals 0, and I want to go to t equals this period time, right? That's how much it takes for me to complete like one full oscillation, essentially. Okay, and this would be like my graph x of t. So let's look up here. So it says for the first part. If the amplitude is doubled, what happens to the total distance that the object travels in one period? So you've probably seen Professor Spilio use different versions of this. So these two equations are the same. So if I have a cosine of wt plus b sine of wt, this just basically allows you to combine the constants here and then deal with this phase shift. So what the phase shift means, say for example, I start at a different position other than maybe t equals 0 for my sine function, right? So for this function right here, right, this would be a cosine, right? Cosine of wt plus pi over 2, okay, from my x of t. If my graph looked like this, why? Why would that be the case, right? Well, if we think about cosine, right? Cosine starts at this. So if this is my amplitude on my graph, right? I have my amplitude goes up here, and then I have a negative amplitude. And then this would be, if I have a spring, the center point would be my equilibrium point. So I'm oscillating up and down throughout my amplitude around an equilibrium point, right? And my amplitude is the displacement of the object originally. And then that spring constant will be pulling it kind of back and forth. That's that oscillation, okay? So if I have an expression that's a cosine function, that means, right, that at 0, my cosine function would equal a, right? So this graph would be slightly different, right? So what does that mean, right? So if I have this pi over 2, that actually means that I am shifting my graph, right? This is the phi, this is the phase shift here. And that's where we see that shift of that pi over 2, okay? So just sort of understanding what's happening here. Okay, so back to our original question here. So we're asked if A is doubled, what happens? Well, if we look at our expression here, right? If our A is the only thing that's doubled, that just means that our distance is going to be doubled, looking at our equation, right? So if we have a larger amplitude, that means that we are oscillating, right? And we're spanning a larger distance for our x function, right? Okay, so all right, for part 2, it says, let's see, what happens to the period, right? So that period is this phi here, right? Or I'm sorry, that the period is our time. The period is our time. This is our phase shift. Sorry, I misspoke. So t is our period here, and this is just sort of our general equation for t. It's sort of rearranged. And we notice that it's not dependent on the amplitude. So the amplitude doesn't affect how long it takes for it to complete an oscillation. What does affect it is the mass and then this spring constant, okay? So we know that our amplitude change does not affect that. Okay, what about the maximum speed of the object? So what happens to the maximum speed of the object if we double the amplitude? Okay, so first of all, how do we get the maximum speed or the magnitude of the maximum velocity? Well, okay, so if we have an expression for distance, which we do here, and we take the derivative of that, we know that the derivative of the distance with respect to time is velocity, just from earlier in kinematics, early in the semester. So we're going to take this function, we're going to take our derivative, right? And this is going to be our derivative. So if we remember kind of like the chain rule here, we're taking this derivative of a cosine of wt, right? And then we actually, so it's going to turn into like negative sine, right? But then we also have this constant on the inside. So it'll be negative sine of wt plus phi, right? Negative a, right? Negative a. But then we do the chain rule, and we also have to multiply by the derivative of the inside, right? Derivative with respect to, so dx over dt, right? For wt plus phi. And then that's going to end up multiplying it by an extra w here. So a w sine of wt. Okay, because we're just taking the derivative with respect to time. So plus phi. So that's our final answer here. So hopefully that makes sense. If you feel rusty on your derivatives, please practice these because you will see these many, many times in this section. So it's important that you feel pretty comfortable with the sine, cosine, trig derivatives. Okay, so all right. So if we know now after we take that derivative, right, this is our answer. We want to find the maximum. So where would that be a max? So I know that sine of any angle, the range for that any sine of x is going to be in between. So it'll be in between 1 and -1, right? So what maximum value of sine of wt would I pick to get the biggest value here? Well, if I choose sine of wt to be -1, that's going to be my biggest maximum. So my biggest maximum is going to be when this Vmax is equal to WA, right? So if I plug in -1, the biggest value that I can get and cancel out that negative, right? This is going to be my Vmax. Okay. So you're going to kind of see this. This might seem like it's a lot. This is going to be a common application to try to find a maximum. Either plug in 1 or -1 to try to get just like the maximum numerical value that you can of a quantity. So we'll see it a couple of times in the different problems here. Okay, so that's my Vmax. Because we're dealing with, we have just simple harmonic motion here. We're going to be using this expression for W just for simple harmonic motion, and we're actually going to go over how we get that later. We're going to derive it and see like if we have different systems where maybe it's not as simple, we can solve for this W. But right now we're just going to take it for granted. Okay, so yeah. So we have this maximum speed. So if the amplitude is doubled, what happens is we're going to double that velocity, right? Because we know that Vmax is just equal to this guy right here, right? Vmax is just equal to WA, so the angular frequency or angular velocity times A. And then this is just going to be the maximum value. Okay, so if we double the amplitude, we double our Vmax. Okay, so there are a couple of other things here that I also included just kind of for, so like if we reduce the mass to 1/4, what happens? Well, we can plug it in this same Vmax equation to see what happens to our maximum velocity. So if we reduce the mass, we also make the velocity, we double our Vmax value, right? We make it 2 times faster if we make a smaller mass and like that still that really high spring constant. If we increase that spring constant, we have more pull back and forth. So if we increase it by 4 times, we can also double our Vmax. So just kind of some conceptual things about how we're manipulating those equations and what that means. And what exactly is happening here, right? So when we say Vmax, if this is my equilibrium point, so like for all intents and purposes, this is 0, the origin for my spring. And then this would be like if my spring was at rest, right? And let's say my spring is connected to a wall here. My displacement, right, is either going to be, so I'll have negative and positive A, right? So this will be some distance that I'm moving back and forth, right? And then my Vmax is going to be my linear speed, right, that I'm shifting back and forth, right? And when we look at the graph, we know that our maximum linear velocity is going to be in the middle here, right, at this equilibrium point. So as that block is going past the middle, it's going to be moving at its fastest speed. It's going to kind of slow down on this end, right, to a full stop here. And then the spring constant's going to push it back. It's going to hit its max speed again in the middle, and then it's going to slow down to a stop, okay, at this maximum displacement on the other side. So it's just oscillating back and forth, right? So we're seeing it move back and forth. Okay, so let's go ahead and move on to an actual problem where we're doing some math to solve. Let's see what the next one is here. Oh, yep, we're going to go through just kind of using some of these equations and how to apply them to some actual problems.